Factor rating relies on our ability to state the relative importance of factors through weights. Now, these weights, in order to compose scores, have to be fractions, but generally when people are talking to you about the relative importance of various factors, they don't talk about fractions. They just say things like, oh, this thing's twice as important as that, and we have to convert that into fractions. That's exactly what this first problem is asking us to do. Let's take a look. Best Purchase must select a location for a new store. Best Purchase has identified 5 factors as important to the store's location. Now with this problem, it lists these. I recommend copying this again as a vertical list. Land cost, they say that's a factor in picking a location. Road access, I'm just pulling these out of the paragraph. Population density is important when picking a location. Average income is important when picking a location, and zoning laws. So they're saying as they try to decide between candidate locations, just counting here that I spotted all of them and recopied all of them. Yes, each of these 5 things is important. Now, what else do they say? Best Purchase feels that each of these factors has the same importance to a new store decision. Okay, with the exception of land cost. Oh, okay, land cost is different from the other 4. How? Which it feels is twice as important to any one of the other 4 factors. In a factor rating analysis, then what weight should they attach to land cost? Okay, so what we're going to determine here is this weight, this fraction, that should be attached to land cost to honor this viewpoint of theirs that it is twice as important as any of these other things, and all these other things, you know, within themselves, they're equally important. Here is a good methodology for doing this. All right, you have a list of things. Look for essentially the lowest common denominator, right? The factor or factors that are the least important. Well, you said these are all equal, and then land cost is twice as important. So that means that this look for the lowest common denominator, it's all these others. Yes. Temporarily assign them a value of 1. Okay, this is not the finished weight. We're just marking, okay, that these were the least important things overall. Still important to Best Purchase. Now, land cost, what's the deal with it? It's more important. It's twice as important as any one of these. So write a 2. So here we have just some whole numbers that reflect in a certain sense how Best Purchase feels about these. We've given a 2 to land cost because it's twice as important to those other things that we gave a 1 to. All right, now we want to turn this into one of those weighting schemes. Next step. Add those numbers. Okay, I'm going to add the list. 2 plus 1 is 3, 4, 5, 6. This adds up to 6. Yes, I need that number 6. Because now I'm going to divide each one of these by that number. That's the weight. We can neaten this list up because land cost, 2 divided by 6 is actually, I'm just reducing it, right? 1/3. Whereas the rest of these, you can't reduce it anymore. It's just 1/6, 1/6. Those are your weights. Those are the weights that you should use later as you are calculating the overall factor rating score of various locations. You should attach a weight of 1/3 to land cost and then 1/6 to each of the other factors. And check this. Remember, the key with weights is that across the entire set of factors, they should add to 1. This will add to 1. Oh, Now, the question was asking what is the weight that you should attach to land cost. So to actually respond to the question, we say with confidence, it should be 1/3, or sometimes people like to speak in percents. It should be 1/3 or 33%. Now, weights are very often the one aspect of factor rating that we kind of worry about the most, like, did we get that right or not? Because they're really what decides who's going to be the winner or who's going to be the loser in terms of like the location being chosen. Now the next problem concerns that worry. It's known formally as sensitivity analysis. This problem is a good example of sensitivity analysis and factor rating. This next problem is also a very good example of some problems look really small and really simple, and they are not. They take a fair amount of analysis and insight to answer them. They're kind of sneaky that way. Okay, let's look at this sneaky problem. A manufacturing firm is choosing between two locations based on factor A and factor B. And then there's information about this. First factor has a score of 10 for first location has a score of 10 for factor A, 90 for factor B, whoa. First off, we do have the critical information right in here, right there, and right there. I'm going to draw a table. I mean, the information's right there, but I don't want to mix these up. So if this was a factor rating study, we'd list the factors over here. This problem looks really simple because you're saying, well, there's just these two factors and they're named A and B. And then we'd have the various candidates as columns in our table, and we only have two candidates. We have this first location, and we have this second location. That's it. Okay. At least now, though, even though it's small, I have a table. I can keep these numbers straight. Because what am I told? The first location scored 10 for factor A. Factor A, first location, 10. And 90 for factor B. The second location scored 90 for factor A and 10 for factor B. Now, the only thing I did here was I just organized the information that we were given in two sentences. All right, I find this a lot easier to work with. Now, this is just information. What's actually asked? Over what range of weights for factor A would this firm select the first location? Notice that in this information, we would also, if this was an actual factor rating study, we would have the weights right there, the weight of factor A, the weight of factor B. The two weights would add to 1, and then that's how we do the multiplication and come up with scores for the first location versus the second location. But they didn't give any information about the weights. They just said over what range of weight. Oh, range. I bet we're going to need to draw a picture. Range of weight for factor A. Okay, this one. Would the firm select the first location? This one. Now, before we go any further with analyzing this numerically, let's just check our understanding. Okay, the first location, because that's the subject of the question, the first location, didn't score very well for factor A, which is also the subject of the question, right? It's the one that got 10 for factor A and then a lot more for factor B. Now, over what range of weights, how important should factor A be that you would pick the first location? Okay, first, our intuition, it'd have to be for very small weights, right? The weights represent the relative importance of the factor. The first location doesn't shine on factor A which means that you'd only pick it if the weight was on the smaller side, right? If the weight of factor B was larger, because the first location does score very well on factor B. Okay, so already this range over which we still would pick the first location, this range of weights for factor A, we're sensing that it would be on the smaller side. Okay, fine. It still doesn't answer the question. To answer the question, I need to think, what is it here that's mysterious? Well, the range of weight for factor A. Yes, I don't have these weights, right? So I am going to choose a symbol to represent the mystery. What is this? X. Let's let X equal factor A's weight. Right? So it'd be like right there. Oh, wait a minute. That means that because, and this is a very handy feature of this problem, because there's only two factors, I automatically know then what the weight would be for factor B, because all factors have to add up to 1. If X, you pick a number, 1/4. If X is the weight for factor A, that means that 1 minus X, or like 3/4, if X was 1/4, has to be the weight for factor B. They have to add up to 1. Okay, and you might be looking at that saying, okay, we're still not any closer to this range of weights that you'd prefer the first location. No, but actually now we have the tool to figure that out. Because look at the question. Select the first location. You would only select the first location if, when you did this arithmetic, this number, mysterious number x times 10, plus 1 minus x times 90, if that result was larger than when you did the same thing over here. Oh, now if you pick different numbers for x, you're going to get different scores, but we can chart this. Let's think about this. The score for first location, we don't know what the weight is, right? But we're saying, okay, we'll let X represent that mystery. That means the score for the first location, if you had a number for X, what would you do with it? You would say 10 times X plus 90 times 1 minus X, right? That's how you would calculate that, versus, and why would you be doing that? Because you wanted to compare it to this, the score for the second location. How would you calculate that? Oh, well, you'd say 90 times X plus 10 times 1 minus X. If we wanted to pick X's at random, say like, just test something like x equals 1/4, substitute in 1/4 here, 1/4 here, 1/4 here, 1/4 here, and whichever one of these two things comes out larger, the larger score, we would pick that particular location. Oh, these are linear expressions. Now, finally now, I see a way to gauge the range of which this essentially would come out larger than this. That's really actually what we're looking for. When would this, when you're picking numbers for x, come out larger than that? Meaning you would select that location. They're linear expressions, so right, what's the grid for? Why don't we draw a picture of our dilemma? Our dilemma is that we don't know this value of x, right? Which is factor A's weight. We don't know it, except we do know something about it. Can't be anything less than 0, and it can't be anything more than 1, because anything on the other side of that is just not rational. Now, we're concerned about the factor rating score of the two locations over different weights. Let's draw that. Now, what do I mean by let's draw that? Pick a location. For instance, the first location here. Okay. The first location. Just say, for instance, that the weight for factor A is 0. I don't know why we would have included it in the study if in fact it has no weight at all, but just say, because the arithmetic is really easy, that the weight is 0. All right, what would be the actual score for the location? We'll put in a 0. 10 times 0, you'd get nothing from that. Plus 90 times 1 minus 0, right, you get all the credit for the other factor. The score that the first location would earn would be, let's see, 10, 20, 30, 40, 50, 60, 70, 80, 90. Would be 90. I'm going to mark that, right? If the weight was 0, the score would be 90. That's what would result from this expression. As opposed to, now I'm just picking another value for x, at the other extreme, 1. What would be the score at the first location if x happened to be 1? Will be 10 times 1 plus 90 times 1 minus 1. All right, this would 0 out. You'd get only credit for that. That's down here. I was letting every grid square be 10. This is a linear expression. I've found 2 points. If you have found 2 points on a straight line, you have found the line. Connect them. Here is what and I have to label it, be careful, first location. Here is a graph of what the first location would score for any other weight that you pick for factor A. Just for instance, if you say, well, I'll pick a weight of 1/2, like halfway in between, follow it up, height of the line, trace it over, that would be the score. Okay, now that's just the first location. The problem is that we're trying to compare the first location to the second location to see which one we'd select. Fine, add the second location to this illustration. Okay, second location. At the second location, if the weight for factor A was 0, what would it score? Well, it'd be 90 times 0 plus 10 times 1 minus 0, or it'd be 10. It would score 10. The second location would score 10 if there was no weight on factor A. Okay, it would score there. And then, well, what if all the weight was on factor A? What if x equals 1? Well, then it would be 90 times 1 plus 10 times 1 minus 1. That would disappear right there, right? It would be 90. All right, if I have found 2 points on a line, I have found that line. I just need to connect them. Here is what and I need to label it, second location would score in a factor rating analysis for the full range of weights that you could possibly attach to this factor A. You say, all right. So what have I learned? Well, remember that the question way back at the beginning is, over what range of weights would you prefer that's why labeling is important, the first location. Well, higher scores are better. So I'm looking for where on this graph the first location is higher than the second, and I see it. It starts at 0. Certainly if there was no weight on factor A, since the first location wasn't particularly talented with respect to factor A, you would definitely prefer it. And it looks like you would prefer it up until a certain point, and then there's some kind of tipping point here of which the second location takes over. And the second location would be your selection. So we would prefer it from 0 to that point right there. So to finish out this question, the only thing that we need to figure out is, okay, maybe I trust my hand-drawn graph, maybe I don't, but what actually is that stopping point? Oh, well, that stopping point would be from a different technique, but it's the same concept. That's a point of indifference. Remember, a point of indifference is a certain, very certain situation over which, if you have like two options, you wouldn't care which one you picked. Now, in this case, we're picking locations based on their factor rating score. At a point of indifference, we wouldn't care between the two locations because they must be earning exactly the same score. That's why we wouldn't care. So we just need to track down what value of x, or the weight on A, what value of x would you coincidentally get exactly the same score at each location? Well, I could do that by saying 10 times x plus 90 times 1 minus x. That's the score at the first location. I just copied this. When does that equal this right here? 90x plus 10 times 1 minus x. Oh, all right. Well, I need to do some simplification here, right? Let's see. This would wind up being 10x plus 90 minus 90x. Whoops, 90x. When does that equal 90x, that right there, plus 10 minus 10x? Whoops, need to clean that up. Let me think. One of the things I could do is subtract 10 from both sides. So I have 80, and then it would disappear over here. Plus I could consolidate these terms, so it's 80 minus 80x. And over here, the 10 disappeared because I subtracted it from both sides. I could consolidate these terms, though, because it's 90x minus 10x. So that is also 80x, which, oh, wait a minute. That means that this is 80. Add 80 to each side, negative 80, or add 80x to each side. Negative 80x would disappear here, 160x. Oh, so x would equal 80 divided by 160. I have just about run out of paper, but wait. 80 divided by 160 is 0.5. My graph actually came out pretty good. It is. It's right over the center. The weight for factor A, at which you stop preferring the first location, is 80 divided by 160, you know what I had down there, or what's that reduced to? 1/2 or 50%. That's exactly where you'd stop preferring that location. Now, with all this scratch work, go back up to the question. What is the actual definitive answer to the question? Over what range of weights? Based on everything that I learned down here, it's from 0 to 1/2. What? Yes, from 0 to 1/2. Over that range of weights, if you calculate the two scores for the two locations, the one for location A will come out larger. You will always prefer that particular location.